Hi, I'm Stefano Petrocchi from the Department of Information Engineering of the University of Pisa in Italy, and I'm pleased to present you my work, a real-time deep learning approach for real-world video anomaly detection made in collaboration with Dr. Giacomo Giorgi from the Institute for Informatics and Telematics of the National Research Council of Italy and Professor Mario Cimino from the Department of Information Engineering of the University of Pisa. This is the presentation outline. I'll start with a brief introduction and then move on to the description of the methodologies proposed. Then I'll describe the experiments carried out and show you their results. Finally, I'll conclude the presentation and talk about some future works perspectives. The advances in information and communication technologies have led to the transformation of the environments in intelligent entities, especially in the video surveillance field. This made possible the development and diffusion of network of cameras. These systems can be enhanced with the use of artificial intelligence in order to enable the autonomous identification of anomalies. Those solutions, however, must face several challenges: the complexity in the detection of very different classes of anomalies in low-quality videos, the need for a timely detection, the need for a lightweight architecture, and the reduction in resource requirements for training, and the ability to investigate network decisions. The first methods of anomaly detection were handcrafted, for instance based on trajectory. Although very effective in identifying specific anomalies, they cannot adapt to categories of abnormalities not previously seen. To overcome these problems, some of the most used approaches are typically semi-supervised. They use only normal videos to train the detector in order to identify anomalies as any deviation from the notion of normality that they have learned. Among the most popular approaches in literature, we can mention autoencoders and generative adversarial networks. Our work is based on a supervised methodology. These methods involve the use of labeled videos in order to approach the problem as a binary classification. Some commonly used neural networks in these environments are 2D and 3D convolutional neural network, often in a two-stream solution using an optical flow stream in parallel with the video stream. These are the main contributions of our work. We propose a novel lightweight deep learning architecture for real-time video anomaly detection that considers contextual, spatial, and motion information. We introduce a novel sigmoidal anomaly score mechanism that produces a more robust score, reducing false positive rate while maintaining a high true positive rate. We defined a new taxonomy for anomalies, dividing them in hard and soft anomalies. We propose a data balancing mechanism to be applied during training, and based on hard mining and an adaptive sampling rate. And finally, we analyzed the learning activity using the GradCam explainability tool to assess which part in the frame contributes the most to anomaly detection, and exploited the results as a tool for anomaly localization in the scene. This is the architecture of our model. This is based on a double-stream network that consists of two ResNet50 that take in input the current frame and the optical flow. The optical flow is calculated between current and previous frame of the video stream. The features extracted from the double-stream network are then concatenated to the bag of objects made using YOLO version 4 object detector on the current frame. The concatenated features are then forwarded to two fully connected layers to produce the classifier anomaly score. In particular, the bag of objects is an array that contains the number of each object detected in the frame for a set of predefined objects. The idea is that in an anomaly detection context, the introduction of information on specific classes of objects may be useful to a classifier that can weight these features against other factors, such as temporal and spatial information. In order to train a ConvNet, it is necessary to subdivide the videos into single-frame samples. The most straightforward solution is to split the videos into single frames respecting the original frame rate. Applying this mechanism, however, we obtain a large amount of redundant data, because two adjacent frames contain only slight differences. thus producing a high overhead during training. A simple solution to this problem is to use a lower frame rate for frame sampling than the original one. This reduces the number of frames extracted from a single video, allowing to train the model on more videos. To maximize the effectiveness of this undersampling technique, it is recommended its use in an adaptive way. A high frame rate is necessary for videos that contain anomalies, to be able to capture even sudden movements, while for normal videos can be used a very low sampling rate since individual movements are less relevant. Generally, anomaly detection problems are characterized by a higher availability of non-anomalous video segments. Moreover, the anomalous class is actually made up of several subclasses, the individual anomalies, which are equally important and must all be recognized by a classifier. Hard mining, therefore, allows for an adaptive sampling of these subclasses in every epoch. Considering using batches of K samples during training, for each batch we sample without replacement alpha K candidates frames, where alpha is a multiplicative factor. Then, an inference operation is performed on the candidates to calculate the losses. After, only the K first sample with greater loss are selected, and finally used as the real batch for training. In our work, we introduced a new taxonomy that divides the anomalies into hard and soft. An hard anomaly is a video segment that clearly contains an ongoing anomaly, like the video you can see on the right. Instead, a soft anomaly is a video segment often preceding or following an hard anomaly in which it is guessable that an anomaly will occur or has occurred, like in the second video. Soft anomalies cannot properly be considered normal segments as they have ambiguous behaviors in them. However, they cannot be considered true anomalies as well, as they do not contain real crimes. Labeling soft anomalies as completely normal or completely anomalous should therefore be avoided in order to improve training quality. In our model, we could use the confidence value of the anomalous class as the anomaly score and alert when this value is higher than a certain alarm threshold. The score, thus computed, however, is very noisy and causes frequent false positives. For this reason, we propose the sigmoidal anomaly score as a novel method for calculating the score. The score, between 0 and 1, is equal to the application of a sigmoidal function s on the value of an accumulator x. The value of the accumulator increases or decreases depending on whether the confidence of the classification is above or below a certain sensibility threshold, tau, decided by the user. A low or high tau value makes the score sensitive to classifications with less or more confidence. Reactivity nu is instead a multiplicative factor that allows to decide how quickly the score grows or decreases. A high value of nu will make the score more sensitive to anomalies that take place in short time intervals, but making false positives due to noise more likely. In our experiments, we used the UCF crime dataset developed by Sultani et al. It consists of long untrimmed surveillance videos which cover 13 real-world anomalies. Annotations in this dataset are provided at video level. In order to train our supervised models, we used the frame-level annotations provided by Landi et al. In UCF crime to local. They created a training set of 210 videos and a test set of 90 videos, with 7 of the 14 original classes with human-related crimes. A series of experiments were carried out to verify the validity of the proposed methodology. The first experiment has as objective to verify bag of objects' impact on anomaly detection. To do so were compared 4 models, a 2-stream and 1-stream networks with the use of bag of objects and a 2-stream and 1-stream networks without its use. The second experiment wants to demonstrate hard mining effectiveness in improving training's quality. Here were compared 2 models, the same 2-stream network with the use of bag of objects as before and another one that not used hard mining during training. The third experiment wants to compare the effects of labeling soft anomalies as normal respect to omitting them during training. We compared 4 models, 2 that label soft anomalies as normal during training and 2 that uses only hard anomalies. In our fourth experiment, we verified the data balancing and soft anomalies omission applicability on an alternative C3D architecture. In our fifth experiment, we wanted to assess the generalization capabilities of our best model on anomalous subclasses not previously seen during training. Finally, in the last experiment, we compared our best model with literature competitors from Landi et al. Research. For this purpose, we retrained our model using the same split of our competitors. It's common in literature to compare models using the area under the rock curve calculated frame by frame. We also introduced a new metric to evaluate the effectiveness of the models in the classification at video level, the video level F1 score. This metric, contrary to the previous, can also be used for weakly labeled test set. For the first experiment, the results confirms that the models that use the bag of objects, 2 S bag and 1 S bag in the table below, have a considerable improvement in accuracy compared to their counterparts that do not use it. The second experiment was also successful, verifying that the use of hard mining has a positive impact on models' accuracy. Also, the third experiment allows to verify that the exclusion of soft anomalies in training, in the bolded models of the table below, improves models' accuracy with respect to their counterparts that use them. The tests on the application of the techniques presented in this work on a 3D architecture have led to good results, opening space for future studies. The results on the generalization capabilities demonstrate that the network maintains almost the same levels of accuracy for unseen anomalous subclasses as for training ones. Therefore, the network was successfully able to learn a general representation of the problem. Finally, the comparison of our best model with respect to literature competitors shows our model as a better frame level AUC, although using a more lightweight architecture and a strong undersampling of the data used during training. In this slide are shown some qualitative results for our best model on testing videos. Orange frame windows indicate a region labeled as anomalous. Light blue regions show sigmoidal anomaly score values. The green line shows classifier's confidence, and the red line shows the threshold above which the value of the score signals the video as anomalous. A, B, and D show anomalous videos where different anomalies are fully identified by our method. It is possible to notice the tendency of the anomaly detector to highlight as anomalous an area greater than the ground truth, since in many cases these contain what we have defined as soft anomalies. E shows a class of anomaly not used during training but correctly detected. C shows the correct response of our method to a normal video, while F shows noise in the classification that is correctly filtered by the sigmoidal anomaly score method. Finally, G and H show a false alarm and a false negative case. For security applications, it is important to verify the video regions that contribute most to anomaly detection, to assess the network's decision-making process and ensure that it has no biases. For this purpose, we can use the GradCam tool introduced by Selvaraju et al. In our model, we can also use the identification of these regions as a method to locate anomalies in progress. For example, in figure, the GradCam highlights the criminal's arm stretching and the resulting optical flow as major contributors to the detection. This paper has proposed a lightweight deep learning approach for real-time detection of real-world anomalies in a video surveillance scenario, addressing anomaly recognition complexity, training efficiency, and model explainability. The proposed approach has a wide margin for improvements in future works. For instance, the contextual information given by the bag of objects can be enriched considering also more relevant objects for the specific anomaly detection task. Moreover, the adaptive sampling rate technique can be extended, for example, by considering the different types of anomalies and their characteristics. And finally, the model could be trained to distinguish soft anomalies as a different suspicious class. Thanks for your attention.